Hi, everyone. Today we're going to work in section 2.2. And just as a quick reminder, in section 2.1, what we looked at was how the first derivative could give us information about a function. So the first derivative could tell us where a function was increasing or decreasing. And the first derivative could also identify maximums and minimums of our function. So today we're going to look at what the second derivative can tell us about a function. So the second derivative is used to determine what's called concavity, or the curvature of a graph. And it can also be used as another way to identify extrema, like the first derivative can. So extrema meaning maxes and mins. So concavity meaning the curvature. So something that curves up, like say a smiley face, something that does a curve up like this would be called concave up. And then a curve that curves down, like a sad face, would be called concave down. So that's the curvature of a graph that the second derivative will help us identify. Okay, and so the information here is in the yellow box. It mentions that when the first derivative is positive on an interval, then the graph will be curving up. And if the second derivative is negative on an interval, the graph will be curving down like a sad face. And so here's a little kind of picture that I think will help you to remember this. So if you notice, the sad face here is for the negative second derivative, and the happy face here for the positive second derivative. Then there's a thing called an inflection point. So an inflection point is a point on the graph where the concavity changes. So where the curving down might switch to curving up. And that becomes an important point. It has some applications and things that we're going to do later. So this inflection point is a key point, and the way we find it is if it's going to be there, it's going to occur where the second derivative is either 0 or undefined. So if you have an inflection point, that's where it will occur at. But that doesn't always mean that if the second derivative is 0, that it's an inflection point. You always have to check it. Okay, so let's just look at a picture and sort of identify this curvature and possible inflection points. So in this intro problem, it says use Desmos to graph, sketch the graph, and then let's estimate inflection points and where concave up and concave down are occurring. So if you want to pause the video here, you can type this into Desmos and take a look. I already have it in Desmos, so let me pull up my Desmos here so you can see the curve that we're speaking of. So what you want to do is look at that curve, and just to get the idea of concavity, you want to look at where it's doing a curve down and where it's doing a happy face curve up, because this particular graph has a section of concave down and concave up. And so therefore it would also have an inflection point, okay? So I'm just going to do a rough sketch of this over here on my paper, and hopefully you're kind of looking at it in Desmos. So if I just do, a basic sketch, again, it's not great, but you're going to see the graph does kind of this, and then it kind of does this like here. And so as far as concave down and up go, where the curvature is down is on this left side of the graph. So it's this left side that would be what we call concave down. It's curving down like a sad face. And then somewhere on that graph, the curvature switches to this happy face. So it's this section in blue that would be what we call concave, oops, let's try to spell that right, concave up. Okay. So you can kind of see the curving up and the curving down. And all we can do at this point is estimate. I'll show you how to find it exactly. But there's some point where this curving down switches to curving up. And so I'll just say, well, it kind of looks like maybe here. And so whatever that point is, that point where you think the curvature changes, that would be what's called an inflection point. Okay, so sometimes we give the inflection point as just an X value, but most of the time we give it as an ordered pair. Okay, so let's make an estimate of it, and then we can state our intervals of, say, concave up and concave down. So again, this estimate is sort of up to you, but let me go look at my picture again, see if I want to make a guess. Well, let's see, on my graph here, I could say maybe the curvature changes somewhere around -2, maybe -2.5. Let's say I'll go with -2 just to make things easy on myself here. So I'm going to guess that at this point when x is -2, that maybe that is where the point of inflection is. Okay, and so therefore I can tell you that what I think is that the graph is concave down on the interval, because remember, we give this interval just like we do with increasing and decreasing. So I would say on the interval from -infinity to -2. And then I would say that this thing is concave up on the interval from -2 off to the x value of infinity. That would be my concave up and down estimates. Again, right now it's an estimate, but I'll actually show you next how we find that. Okay, so now you kind of have the idea of what the curvature down and the curvature up is. Okay, so now what we're going to do in example 2 is actually find this point exactly, see if our guess is right, I don't know, and then verify kind of what we're seeing in the graph above. Okay, so here's how calculus would look for this. So let's take our function, and we mentioned that if you're going to determine concavity, then you have to get the second derivative of your function. And so that's what we're going to do, is take this function and jump all the way to our second derivative. Okay, so to do that, we first have to get the first derivative. So let's get first derivative. So f prime of this function, let's see, 3 times 2/3 will be 2x, lower it by 1 squared. 2 times 4 makes 8x to the first, and the derivative of 3x is just 3. Now move on to the second derivative, because I'm not interested in increasing or decreasing. I want the second derivative to identify concavity. Okay, so second derivative, 2 times 2 is 4x, and 1 times 8 is 8, x to the 0. All right, here's my second derivative. So if you want to find an inflection point, we start by setting the second derivative equal to 0. Okay, so to find, and I'm going to say it this way, possible inflection points, we're going to set our second derivative to 0. All right, so 0 equals 4x plus 8. Let's solve for x. All right, throw in the 8 over -8 equals 4x. Let's divide by 4. Look at that. I get x equals -2. Now, I can't guarantee that's an inflection point until I test it. So this is a possible inflection point. I like to call it a PIP, P-I-P, possible inflection point. Now, how do I know if it's for sure an inflection point? I do a little test like we did with the first derivative. So I'm going to make a little number line here. I'm going to label my number line the second derivative. Okay, that's important because I'm going to look at second derivative values. I put my possible inflection point on here, and then I test. Now you see, this should be very familiar, like what we did with our first derivative. Okay, so pick a point on each side of -2, and let's see if the second derivative is positive or negative. So remember, second derivative. So let's say on the left side of -2, maybe I pick -3, and let's go over on the other side, the right side, and maybe pick 0. And again, we're going to plug into the second derivative. Okay, so -3 in the second derivative will give me 4 times -3 plus 8. Now that turns out to be what, -12 plus 8. Okay, that's going to be negative. So that tells me that to the left of -2, I have a negative second derivative. And remember, this is a second derivative. So what that tells me when it's negative, remember, sad face, concave down. Okay, so I'm in a concave down section of the graph. If you plug 0 in your second derivative, 4 times 0 plus 8, okay, that's going to be 8, which is a positive value. So that tells me my second derivative is positive on the right side of -2. So remember, positive, smiling face, you're happy. Okay, so this verifies then that -2 is indeed where the concavity changes. So it is for sure an inflection point. Okay. And that's actually what I saw in my picture anyhow, right? This does verify what we saw in the picture. So I can definitely conclude that my concavity is down. So I'm going to say concave down in this section of -infinity to -2. And I can for sure tell you that is concave up on -2 to infinity. Now let's give the actual inflection point, because it's a point. So let's get the whole ordered pair, -2 something, right? Let's get the ordered pair. So I need to get the y value for my inflection point. Remember, it's a point on the graph. So if you want the y value, you need to plug that x value back into the original, right? In the original. So we have to take -2 and plug it into the original function, f of -2, back in the original. Okay, so if you do that, I know it's a little bit messy, but we have a calculator. So just plug it in. So I'll write it out what I'm plugging in. -2 is going back into that original function. And I just type it in my calc and I hit enter. And you know what I get? I get 29/3. And I want to keep it as an exact value. Don't give a decimal when you can be exact. So this is my exact inflection point that if I look above on the Desmos picture should look about right. Okay. So that is how we test for concavity and how we find inflection points. We do pretty much the same process that we did with the first derivative for increasing and decreasing. All right. Okay, let's try another example. So example 2 says, here's a function. Use your calculus techniques to determine intervals of increasing, decreasing, concave up, concave down. Okay, so this means I get to practice my first derivative stuff and my second derivative stuff. Okay, I get to practice section 2.1 and our new information. All right, so let's just start with first derivative stuff. So I'm going to get my first derivative here, f prime of x. So the first derivative of 80 is 0. And then let's see, 2 times -8, or I'm sorry, 2 times -9, -18x minus, let's see, 3x squared. That's my first derivative. Let's get our second derivative. Should we do that now or wait? Well, we could do it. Well, let's wait. I'll set this equal to 0 first. Let me find my increasing and decreasing. So let's factor. How about we take out a -3 and an x? And when I do that, let's see, divide in there, be 6. This will turn into plus x. Okay, make sure I did that right. Wait, yeah, 6 plus x. Yeah, looks good. Okay, so now let's set each of these equal to 0. So -3x, if you set that equal to 0, is just going to give 0. And if we take 6 plus x and set that equal to 0, we should get x is -6. Okay, so those are our critical points, right? That's what we call these guys. Critical points. These are the possible maximums or minimums, but I'm not interested in that on this problem. I'm really just interested in increasing and decreasing, but I still do that process. So let's take a number line. Let's label it first derivative. Let's put our 0 and our -6 on here. And then I'm going to pick points and I'm going to plug them in my first derivative. And I'm going to see where the increasing and decreasing is. Because remember, increasing and decreasing comes from the first derivative information. Okay, so I'll pick some test points. I don't know, maybe -7. Let's say we pick -1, and maybe we pick 1, and we plug them into the first derivative. Okay, so I'm going to pause here and let you work this, and then we'll come back and you can check it. So do your plugging in, determine whether you're going up or down. Okay, let's take a look. So here's what I found. I plugged my test points here into my derivative, and I found a negative, positive, negative. And so that tells me where it's going down, up, and down. And so then here is my final conclusion. Remember what the problem asked for. It says, where is it decreasing and increasing? And here it is. So I'm just labeling this using my number line to, get my information. Okay, so now the second part of the problem was, well, where's the concavity? So all I'm going to do is kind of repeat the same process, but with the second derivative. So you see how kind of this process is very similar. Okay, so let's do that. Let's get our second derivative, and then we will find out about concavity with that. So now I'll know where it goes up and down and how the curvature is. Okay, so second derivative, let's see. Derivative of -18x is -18, and the derivative of 3x squared is -6x. Okay, so let's set that equal to 0. And then let's factor this. Or I suppose, well, we could just not factor since we just have a linear equation. Why don't we just solve for x here? Let's throw my 6x to the other side here. Let's not make it complicated. How about 6x will equal -18? And if I divide by 6, how about -3? So remember what this is. This is your possible inflection point. Now on this problem, it didn't ask me to actually find inflection points, but I need this to figure out concavity. All right, so I do another number line. However, this number line, be sure to label it the second derivative. Okay, it's important you label these number lines so you don't get lost on what's what here or where to plug your numbers in. So I'm going to be plugging values into the second derivative here. I'm going to pick a number bigger than -3. So maybe I'll test 0. Pick a number smaller than -3, maybe -4. Plug them in the second derivative. Okay. All right. So I could do this pretty quick. So the second derivative, if you plug in 0, it's going to give you -18 minus 6 times 0. That's going to be a negative. Okay. So again, pause the video. Do this on your own if you can. If I plug -4 in my second derivative, that looks like I'm going to end up with -18. It's going to end up with a +24. That's a positive value. Positive value. So remember what these mean. These tell you curvature. So the positive second derivative is telling you happy face curving. The negative is telling you sad face curvature. Now I can identify my concavity. And by the way, I know that -3 is an inflection point, although it didn't ask for that. Okay, so let's do it. So we have concave up from -infinity until -3, right? From all the way out here on our number line to there. And then we have concave down. That's going to be starting at -3 and heading off to the x values of infinity. And that right there should answer all their questions. Now, there's so much more they could ask. They could say, what's the inflection point? What's the max or the min? And actually all that information is all right here for us. I just didn't give that because it didn't ask for it. Okay, but it's definitely available. And I hope you can kind of see that. Okay, so I'm going to pause and stop the video here and then start another one. So this will get you through at least the first part of determining concavity. All right, hope this has been helpful.